You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Tara Murphy. Dr. Tara Murphy is a professor at the University of Sydney and associate investigator in the Osgrav Centre of Excellence. Professor Murphy's research is in radio transients, and she is the co-lead of the transient projects on the Australian SKA Pathfinder. Dr. Murphy also teaches computational science and data science for physics and astronomy students.
Dr. Tara Murphy, welcome to the program.
It's great to be here.
Now, Doctor, there's been an interesting development, strange radio signals emanating from near the center of the galaxy. But before we get to those, the Australian Square Kilometre Array Pathfinder, ASKAP, what is the idea behind that radio telescope array?
So ASKAP is a group of antennas located in Western Australia, and it was designed to be a really fast survey instrument. So radio telescopes detect radio waves. So in other words, electromagnetic radiation in the hundreds of megahertz to gigahertz band. And ASKAP operates at about a gigahertz most of the time. So ASKAP has the special thing about ASKAP, well, there's lots of special things, but maybe the most special thing is it has a very wide field of view. So it can see 30 square degrees on the sky at any time. And if you think about that, the size of the full moon on the sky is about half a degree. And so this is 30 square degrees in one go. What that means is it can look at the sky very quickly. It can survey the whole sky, pointing at every single bit in order. And because it can do that very quickly, it means it can do it many times. And that's very new for this kind of telescope.
Now, what does that mean for resolution? So if you have that wide of a field of view, does it lower the individual resolution of the source objects?
In the past, that's been true. The telescopes with the wider field of view have typically compromised on resolution. But ASKAP actually has pretty good resolution, so comparable to our best radio surveys so far, and at the same time has a wide field of view, which means that we get this really detailed picture of the sky at radio wavelengths. And for what I do, looking at radio transients, what's important is that we can observe the sky repeatedly. So because we can do it fast, which we haven't been able to do in the past, we can now look at the whole sky and then go back the next week or the next month and look at the whole sky again. One of the surveys I worked on early in my career, it took us 10 years to do what ASKAP can do in a few days.
That's amazing. So it's basically an all-sky survey telescope in radio, sort of like what the LSST Vera Rubin Observatory is going to be for optical, right?
Yeah, that's right. So just like the LSST Rubin Observatory, that's the next generation of the optical survey machine. And ASKAP is one of the wave of next generation. I mean, we should stop calling it next generation because it's here now. But this new wave of radio telescopes, there's ASKAP in Australia, there's Meerkat in South Africa, and there's the upgraded VLA in the US. And between them, they are doing things that we haven't been able to do before in radio astronomy. Of course, they're all leading towards the Square Kilometre Array, which is the big, that's what will really revolutionize radio astronomy.
Now, what is the timetable for that? Now we have the Pathfinder, but the actual Square Kilometre Array, when will that see first light, so to speak?
That's right. I don't have the timeline in my head, but construction has started in both Australia and South Africa. They're hiring a lot of engineers and people to actually roll out the telescope. So the phase 1 square kilometre array construction is underway. I can't remember the timeline for delivery, but we should be able to see an operating, at least, phase 1 telescope within a few years now.
It's happening. Now, what is the implications for things like SETI with this capability of being able to see wide field like that? Can SETI researchers looking in radio make use of that?
Yeah, so first up, I would just emphasize I'm not actually involved in SETI and I'm not an expert on that. But it's true that SETI uses the same kind of telescopes, radio telescopes, as what I use for my research. And one of the really cool things about SETI is that you can operate in what's called piggybacking mode or commensal mode, which means that whatever we're studying from an astronomy point of view, SETI researchers can piggyback on that and look for interesting signals, that satisfy their criteria. So in the past, as I said, because they've got the telescopes have got a smaller field of view, that has sort of limited how many things that you can look at any given time. But with this next generation of telescopes, with ASKAP and with the square kilometre array, we can look at thousands of stars at the same time. What SETI is mostly interested in is monitoring nearby stars in our galaxy. And so that's also actually what I'm interested in for different reasons. And so they would be able to look for signals from thousands and thousands and ultimately millions of stars in our local neighborhood.
Now, radio transients. This is things like fast radio bursts and odd radio circles and all these things that have been noticed in radio as radio astronomy has progressed. Now, being able to see a field of view like that is good for picking up transients, right?
That's right. So the challenge of radio transients is in the name. The fact that they're transient means that they're not visible all of the time. That could mean that they're periodic, they turn off and on, or they're rotating, or it could mean that they're actually off for long periods of time and only occasionally you see them. So the challenge of finding things that are transient is that if you just look up at the sky on any given night, on any given moment, the chances are you're not going to see them. And so we know that we've almost certainly missed many of these objects with past surveys because we only looked at the sky once in that spot. Or we looked at the sky many times, but with a telescope that wasn't very sensitive. So the challenge of all of those types of transient objects, whether they're extremely fast ones like fast radio bursts, or whether they're much slower evolving things like the afterglow from a gamma ray burst or a supernova, which evolve over months. In either case, whether you're talking extremely fast or extremely slow, it's hard to find them if you only look once. And so being able to look at the sky many times, repeatedly in the same spot, is critical for finding them.
So this is also opens up the idea of what about very long-term transients, meaning that, say, you see something and you don't see it again for 8 months or a year or something like that. Those types of transients we wouldn't be likely to see through standard methods, but now we might be able to see stuff that occurs on those periods, right?
That's right. So a really good example of a long-term transient that people have been searching for many years and only just starting to get the inkling that we might have found some is called orphan afterglows. And this is related to the phenomenon of gamma ray bursts. So gamma ray bursts are extremely energetic explosions. They're in fact the most energetic explosions we know of in the universe, maybe except for the Big Bang itself. And so these energetic explosions create firstly a short term, so gamma ray emission that happens instantly, but then they also have, I shouldn't say instantly, it happens extremely rapidly during and after the explosion. But then they have what's called an afterglow as the material from the explosion travels out into the interstellar medium, it causes a shock, and then we detect in radio astronomy, we detect the accelerated electrons that are accelerated to relativistic speeds in the magnetic field, we detect them on Earth. But that process, that expansion into the interstellar medium and so on, that takes months to happen. So with gamma ray bursts so far, we only see the gamma ray burst if the very narrow beamed gamma radiation happens to be pointing towards Earth. But we know there are many more of these objects where the beam is not pointing towards Earth, and so far they have essentially been invisible. But now that we can do these surveys in both optical and radio, very sensitive, and we know that the afterglow is much more isotropic than the beamed initial emission, it means that we can detect, say, gamma ray bursts where we haven't seen the original gamma ray burst at all, and hence we call them an orphan afterglow. So an orphan afterglow is something in radio that evolves over month-long timescales, over many months. And so that is very hard to detect if you've only looked at the sky once. You need to look at the sky ideally every few weeks or every month to look for those things that are changing. And that's exactly what we're going to be doing in these surveys.
Now, the gamma ray bursts, the mysterious gamma ray bursts, what's the best model for that? Is it like a neutron star merger or something like that? What's the consensus on what it could be?
Yeah, the gamma ray bursts were one of astronomy's big mysteries for a long time. They were initially discovered. It's actually a really interesting story. We can't go into the whole thing here probably, but they were discovered back in the period where the US was monitoring the anti-nuclear test ban treaty, and they launched the Vela satellites to look for gamma ray emission on Earth, because that's one of the side products of a nuclear explosion. And what they detected was actually these enormous gamma ray emission explosions coming from space. And so for a long time, these were a complete mystery. But then the advent of optical telescopes to follow up these objects located them to host galaxies, and eventually determined that most of these gamma ray bursts were coming from the death of a massive star. So a bit like a supernova, where a massive star gets to the end of its life, it's burnt up all of its fuel, its core collapses, it expels all the remaining material out into the interstellar medium, and if it's highly magnetized, has a very narrow beam of gamma ray emission come out. So that explained one group of gamma ray bursts called long gamma ray bursts. But then there was a different group of gamma ray bursts called short gamma ray bursts. The gamma emission lasted for a much shorter period of time, and they remained a mystery. The main hypothesis was that they were a neutron star merger, and that was in fact confirmed by the the 2017 discovery of a neutron star merger by LIGO in gravitational waves, and that was shown to have the properties of a short gamma ray burst. So we know that gamma ray bursts are caused by two things: the death of a massive star and the merger of two neutron stars. So the death of a massive star is the most energetic event, and then the merger of the two neutron stars is still extremely energetic, but a bit less energetic than a long gamma ray burst. So that's actually a mystery that's only recently been solved.
That's interesting. Now, the Vela satellites that originally detected these were basically spy satellites. Was that information classified? I mean, did they see that and say, we don't know what that is, but this is a classified satellite, so we can't tell anybody? So what is this? Was it a sort of serendipitous, accidental scientific discovery that spent some time classified?
You know what? I can't remember whether that initial discovery was classified. It was certainly published quite early. I believe the scientists involved knew very early on that these couldn't possibly be from Earth, because the energy level that they were observing was far too high to be anything, human-created nuclear explosion. So they were published very early on. I can't remember if there was a period of classification, but I can send you an article afterwards about it. Someone's written a really nice history of this, one of the original authors. And it's really fascinating because it's a completely serendipitous discovery. We talk a lot about serendipitous discoveries in science, and this was really one that was completely unexpected.
That's the good stuff, though. Serendipitous discoveries and the discrepancies. That's where the fun is. Now, we have something new. Something rather disconcerting, actually. New discovered radio sources coming from near the center of the galaxy. Now, before we get to that, I want to ask you this. Is the center of the galaxy like really noisy because of the compacted nature of everything? Or is it actually fairly straightforward to weed out, different radio signals?
The center of the galaxy is extremely dense, so it's a busy place. There are an enormous number of stars, there is a lot of dust, and that means that when you look at it with an optical telescope, it's actually quite hard to see all the different objects because the light is attenuated by all of the dust at the center of the galaxy. One of the great things about radio telescopes is that because the wavelength of light you're looking at, and I use light, we often use light quite generally to mean electromagnetic radiation. So I'm talking about radio light. The wavelengths are much longer. So if you think about the wavelength of optical light that you're detecting, it's hundreds of nanometers. But the wavelength of radio light is centimeters to meters. And so that radio light, radio emission, can travel through the dust towards the center of our galaxy in a way that optical light can't. And so one of the cool things about radio telescopes is that we can see into these dense regions. Of course, we can't see the same things. So that's a really important part of this story, is that when you look in optical light, you're seeing mostly thermal emission. You're seeing things that get hot, like stars. But when you look at radio, you're usually seeing a different emission mechanism. So you're seeing things like, for example, synchrotron radiation, where electrons have been accelerated in a magnetic field. So I won't get distracted by that side topic of what is radio emission. The point is, when you look towards the center of our galaxy, it is a very busy place. It's dense, it's full of stars, and that's actually one of the reasons we pointed that way, to look for transients, because we know there's a lot going on there. We know there's a lot of stars there, and hence a lot of energetic processes on stars could be happening.
So in other words, when you're looking for something rare, look in the dense areas and you have a higher chance of seeing it.
That is one strategy, yes. And so that was the strategy we were using. There have also been some mysterious radio sources detected towards the center of the galaxy before, and we'll probably get to that later. So that was one of our motivations, to see if we could find something like those mysterious sources, and we did.
Now, those mysterious sources, what do they look like? I mean, are these like broadband emissions, and where are they on the radio spectrum?
Yeah, so ASKAP, the central frequency that we were using with ASKAP was 888 megahertz. So we're talking about gigahertz frequencies. And the bandwidth of ASKAP is about 288 megahertz, so roughly about 300 megahertz. When we're looking at astronomical radio sources, they almost always occur over a very wide bandwidth, so hundreds of megahertz, gigahertz. So we were looking towards the center of the galaxy, and we were looking at about a gigahertz. And what we were looking for were things that changed very rapidly between our images. So we make an image of the sky, in this case, some regions pointing towards the center of the galaxy. We make an image of that, and then we go back, in this case, about a month later, and we make another image. And then we look through all of the astronomical objects in that image, and we look for things that have changed a lot between one image and the next image. So the first strange property of this source we found was that it changed very rapidly. In this particular case, we started monitoring this field in April 2019, and there was nothing at the particular location of this object until suddenly in January 2020 it appeared. So we had quite a number of observations with no detection, and then suddenly quite a bright detection.
And what's the working hypothesis on what it could be? Is it, again, another situation with a neutron star or something like that? I mean, could there be, I don't know, a magnetic field anomaly or something like that causes it?
Yeah, so the next bit of information, the first bit of information we had is that it changed quite rapidly. And that could be any number of different things. So it was enough to be interesting, but it didn't seem that unusual at that point. The next piece of information was that it had circularly polarized radiation. And I won't get into the technical details, but it's very rare to see circularly polarized light from an astronomical object. that is only a very few classes of objects exhibit that. And one of them is neutron stars. So they are often circularly polarized, light from them, the radio light. And another is flaring stars. So we started looking at those two options. Firstly, with a flaring star. So you know that our own sun has flares on it, solar flares we call them, obviously, because they're from our sun. We know that smaller, cooler stars called M-dwarf stars actually have flares that are thousands of times stronger than the ones from our sun. And so one of the and they also are circularly polarized. So one of the things that we thought it could be is a flaring star towards the center of our galaxy. We know there are lots of stars there, so that makes sense. But for a star to be flaring that brightly, we can estimate how bright it should be in optical light. When we look with optical telescopes, we don't see anything that's there. So if it is a star, it must be an extremely, extremely cool star that is so faint that it's not visible with the telescopes that we used. And so we pretty much ruled out the option that it was a flaring star. So then the second type of object that is often circularly polarized are pulsars, which are neutron stars. And as you might know, neutron stars are the remnants of a dead star, basically at the end of its life. They're the densest objects we know in the universe, and they rotate extremely rapidly. So they rotate between seconds and milliseconds. They can actually do a full rotation in that time. So I find that quite hard to imagine, actually, that something, as massive as the sun can rotate in seconds or even milliseconds. So now with a pulsar, it's not that it's switching off and on, it's that it has beamed radio emission coming out of its poles, and as it rotates, it's like a lighthouse. We only see that emission if it happens to be pointing towards us. So one theory is that it could be a pulsar. Now, we observed this object with Parkes, so this is all part of the detective story. Parkes is a famous Australian radio telescope that is often used to find pulsars. And it's when we observed it with Parkes, there was no pulses. So the characteristic of pulsars is they have these millisecond or second pulses that you can detect with a particular telescope mode. And we didn't detect any. But there was a bit of an ambiguity because we knew that this object was also not visible, not switched off for months at a time. So what if when we observed it with Parkes, it was just off and that's why we couldn't see the pulses? So that led us to the next bit of the story, how to work out whether there were pulses coming from this object and hence whether it could be some kind of neutron star. And so we went to the Meerkat telescope in South Africa because that has a mode where you can observe both imaging and pulsar mode at the same time. And so we started monitoring it with Meerkat, just doing a very short observation every couple of weeks. And so we monitored it through November 2020 and December 2020 and January 2021, and we didn't detect anything. And then in February 2021, we detected it with Meerkat. And so that was great. We were starting to, doubt ourselves there with months of non-detection. We detected it with Meerkat, and that meant that we got the pulsar mode observations at the same time. When we checked them, there were no pulses. So this object seems to have all the properties of a pulsar, but not have any pulses, which is the main property that you associate with pulsars. And hence, we were left with a bit of a mystery.
It's hard to envision what that could be, but it has been noted with pulsars that there are a few of them that just stop, for a period. And there's one of them, I think, stopped for over 500 days and then all of a sudden switched back on. So you wonder if it's something going on with the intense magnetic field of that pulsar, some irregularity, or maybe it's changed directions of where the beam's pointing or something like that. So is that the best guess still, though, with this particular strange signal? Is pulsars are probably the key?
Yeah, I think so. So we have there are 3 other objects that have been discovered towards the galactic center. And when I say towards the galactic center, it is important to clarify that I don't mean directly towards. If you look directly towards the galactic center, it's what you'll see in radio is the supermassive black hole at the center of our galaxy, Sagittarius A star, Sag A Star. And so we're not talking about directly towards, we're talking about within a few degrees. And if you look within a few degrees of the galactic center, there have been 3 other objects discovered in the past with broadly similar properties. And they have been called galactic center radio transients. Now, that's one of those descriptive names that scientists use when we don't really know what it is. It's not based on our understanding of the physics of what's going on here. It's just it's a galactic center radio transient is a group of things that we don't actually understand. And all of those objects share broadly the same properties, but none of the properties are exactly the same. So none of them are the same as each other. But they're all different to everything else we know. So we're saying that our object is broadly, it could be considered a galactic center radio transient, but that doesn't actually help us very much in knowing what it is. So then that leads us to your question, which is what could this our object and also galactic center radio transients more broadly be? And I think, yes, that most of the theories are that there's some form of unusual neutron star or pulsar with a strong magnetic field, with some kind of intermittent behavior that is caused by something unusual. It could be objects that are in a binary or triple system and also have some eclipsing, also have some intermittency. It could be a pulsar or neutron star that's dying even more than it's already the dead remnants of the star, but is further dying, and its pulses are switching off. But you have to be able to explain why we can't actually see the pulses when it's on. And so in a way, our observations provide some new information on that front, because we've actually got these joint observations in imaging mode, so we know it's on, and pulsar mode, which show there's no pulses. So it's pretty tricky to explain all of the different things we see. And I think this is one of those cases where, I hate to say it, but what we need is more objects like this, so that rather than being able to just sort of do the detective work on one, we can look at the whole population of them. And that's how most of these mysteries were solved in the past. It's how gamma ray bursts were solved, and it's how fast radio bursts are in the process of being solved.
That's a common theme throughout astronomy. Always look for more examples, and then you get a better sampling, and then you can understand it as a whole. Now, you said something that piqued my interest. If you look in radio at the center of the galaxy, you see the supermassive black hole, Sagittarius A star. Is that like an elephant in the room in radio? I mean, is it completely useless to look in that general area because that thing's so radio bright?
It does make it hard to see details in that area. So it is very bright in the radio, and it also has a lot of extended emission, which always makes it hard in radio astronomy to do the imaging, because the imaging is actually not the same as with an optical telescope, where you're literally collecting photons in a very similar way to your camera does. In radio astronomy, you're creating an image by Fourier transforming the sky. And so whenever you have extended emission, it makes it very hard to form images and look for transient sources. So if you, I'm sure you might have seen images from either ASKAP or MeerKAT of the center of our galaxy, and you will see that it's a very busy, messy place in radio. However, because what we're looking for are transient objects, they're very compact. And so that means compact means very small on the sky. And so what we can do is some tricks like remove the extended emission by applying a kind of filter in our imaging process. This is then, signal processing kind of techniques. We can apply a filter to remove the extended emission and only be left with the compact emission. And so we can actually get rid of most of the problems associated with looking towards the center of our galaxy if we're looking for things that are changing.
Now, just out of curiosity, so the radio emissions from the supermassive black hole, is that being caused by the accretion disk, or is it something to do with the black hole itself?
Yes, so it's the accretion disk. If you imagine the supermassive black hole at the center of a galaxy, you've got all of this material. I'm sure you've seen the stories of stars that are falling into the black hole at the center of our own galaxy. So they're accreting material, and this material forms a disk of gas and dust and stars and so on as it gets close to the black hole. Another thing that happens with that accretion disk, because of the alignment of the magnetic fields, is that you get some material being propelled out of if you imagine the sort of poles of the accretion disk. So if you imagine the accretion disk in one plane, and then in the perpendicular plane to that, you imagine jets of material coming out of that system. Those jets accelerate the particles to relativistic speeds, and in that process of acceleration, the particles emit synchrotron radiation, and it's synchrotron radiation that a radio telescope detects. So we see the effects of the black hole. That's what we see in radio. So when we look at other galaxies, in fact, when we look at the sky with ASKAP, if we just take any image of the sky at radio wavelengths with any radio telescope, what you see is little blobs all over the sky. Almost all of those little blobs are what's called AGN, active galactic nuclei, and they are the supermassive black holes at the center of other galaxies that you're seeing. So if a recent result from ASKAP, the Rapid ASKAP Continuum Survey, was like a shallow survey of the whole sky that ASKAP can see. So the whole southern hemisphere plus up to a declination of plus 50 degrees, so almost the whole sky. Then it detected about 2.5 million objects, and almost all of those objects are supermassive black holes at the center of other galaxies. We don't actually, we can see the star formation, but the dominant effect in bright radio detections is active galactic nuclei, AGN.
That's amazing. So they would actually be very common if you see that many of them. So giant supermassive black holes are normal for this universe, even though as we envision them, they're very wildly violent, crazy places, but that's the universe. And the real weird thing is this planet where we're living on. We're weirder than the supermassive black hole because we have, life. Now, what's the future? So now that you found this object and you're going to look for other examples, where are you going to look? Are you going to continue to look near the center of the galaxy, or are you going to try and find a sampling, elsewhere in the galaxy?
So this result came from the pilot surveys from ASKAP. So in the last 2 years, we've had 200 hours on the telescope, and we've already found these amazing things like this unknown object and also lots of new radio stars and so on. Now, in next year, the full ASKAP survey starts, and we're hoping to spend thousands and thousands of hours looking at the sky. So we're hoping that this is just the start. Now, where will we look? We're just planning our survey now. In fact, we're about to submit the time allocation proposal next week. So this is very timely, this interview. And so we've just designed our full survey. We'll be splitting our time between looking at the extragalactic sky. And what I mean by that is looking away from the center of the galaxy so that we can see things like we spoke at the beginning of the interview about gamma ray burst afterglows and supernova afterglows. Those things, we don't want the galaxy getting in the way. So if we try to look for them towards the center of our galaxy, that doesn't make any sense because all of the things in our galaxy, the stars, the pulsars, and so on, they get in the way of detecting those. So some of our time will be spent looking out beyond our galaxy into distant space and looking for what we call cosmological explosions. So things like the gamma ray bursts that are a long, long way away, and they can help us understand the behavior of some of the first stars and some of these extreme events like neutron star mergers in other galaxies. Some of the time in our survey, we will be focused on the galactic center and also along the galactic plane. So the galactic plane is the region, if you're thinking about our galaxy and you know that it's kind of UFO shaped, there's the bulge in the center of the galaxy, which is what we were talking about before, the really dense area, lots of stars, lots of dust. And then there's the disk of our galaxy, which is much thinner, so on the sky, takes up about 10 degrees. And that's the disk. That's when you're out at night away from the city and you look up at the sky and you see the band of the Milky Way, across the sky. You see on the sky the cloudiness and the extra stars and so on in that band. That band is looking into the disk of the galaxy. And so we will be spending quite a bit of our survey time looking into the galactic center and the disk of our galaxy to look for those objects that we discussed, like neutron stars in our own galaxy and flaring stars in our own galaxy, and things like these mystery objects, because we know that's a good place to look for them. So we will be trying to cover all bases. We'll be looking for both those long timescale things, we'll be looking for super fast things, we'll be looking for flaring stars, we'll be looking for dying neutron stars. It's pretty exciting because everything that's changing rapidly means there's some kind of extreme physics happening. It means there's an extremely energetic process. And it means that there's something quite unusual happening because most astronomical objects are not changing on these rapid timescales. So that's the aim of our survey. It's called the ASKAP Variables and Slow Transient Survey. And we'll be looking for all of those phenomena and more.
Now, when you collect that data, can the SETI people look for artificial signals, like super narrowband signals, or is the equipment just not looking for that?
So SETI can piggyback on any observations, and one of the great things about ASKAP is that all of the data from ASKAP will be made public straight away. So as soon as it's been validated as being reasonable quality, it will be released, and anyone in the world can use it for anything. So I'm sure that SETI would be interested in this kind of public data set. Now, one of the things that we touched on a bit but didn't discuss more is the idea of what kind of thing would they be looking for compared to what we're looking for. And I think I mentioned that with astronomical objects, for example, your flaring star, what you're usually seeing is broadband emission. So this is radio emission that is reasonably consistent across hundreds of megahertz and even gigahertz, which means that if you even observe it with a different telescope, for example, a low frequency telescope like the MWA or LOFAR, they operate at hundreds of megahertz frequencies. Or if you observe it with a telescope that can do higher frequency, for example, the JVLA in the US or the Australia Telescope Compact Array in Australia, they can do up to, say, 10 or 20 gigahertz. Most of the astronomical objects I talked about, such as gamma ray burst afterglows, active galactic nuclei, flaring stars, they occur over a massive bandwidth like that of hundreds of megahertz to gigahertz. But we assume that most artificial signals are in fact very narrowband. So just to give you an example, and again, I'm not a SETI expert, but a very simple example is a FM radio that we generate on Earth. Obviously, that's an artificial signal. It's typically got a bandwidth of 0.2 megahertz. So rather than having a emission bandwidth of gigahertz, it's 0.2 megahertz. And so typically a lot of the signals that SETI researchers look for in radio data is very narrowband signals. And that's one of the signs that it would be an artificial signal. So that's the kind of signal you could look for in all of this radio data that we'll be making public.
Out of curiosity, and this may be a stupid question on my part, the polarization of the radio waves. Now, can gas and dust polarize a radio signal? So if you have something that's sitting inside of a nebula or something like that, can that effect happen in that situation?
Usually gas and dust actually has the opposite effect. So it randomizes the polarization more. So if you think about light that you typically observe, it isn't polarized. You're seeing it. So what does polarization mean? Okay, an electromagnetic signal is called electromagnetic because there's a magnetic field and electric field that are perpendicular to each other. And so when you see polarized light, linearly polarized light, it means that the electric field vector of that light that's coming towards you is aligned. So you have all of the light aligned in one way, the electromagnetic wave. If you have a circularly polarized signal, it means that it's aligned, but that vector of alignment is rotating as it comes towards you. So most things like gas and dust actually have the effect of depolarizing, not polarizing light. So the light we're looking at that's highly polarized, it usually means that it comes from a physical process that generates polarized light, and then various things can depolarize it on its journey.
Now the source polarized, right? Or not polarized, but it was polarized, but it rotated, right? Could you explain that?
So the light that we're seeing from this source is circularly polarized. Now, most light that you see isn't polarized. And what polarization means is that the electromagnetic field vectors that cause electromagnetic radiation, in linear polarization, the electric field vector is aligned in a given plane. So that means that the light, in a sense, is aligned in one direction as it's traveling towards us. Now, with circular polarization, that's a special case. It means the electric field vector is in a given plane, but that plane is rotating as the light travels towards us. To detect polarization, you need a telescope that can detect two perpendicular directions of light. And so when it arrives, we can tell by combining those signals whether the light is linearly polarized or whether it's circularly polarized. A majority of objects are not circularly polarized at all. It's very rare to find some that are. Now, it's not a perfect analogy, but thinking about polarization detection is a little bit like wearing sunglasses. So when you're outside, the light from the sun is unpolarized, and when you put sunglasses on, it makes the light that you see less bright, less of it hits your eyes. And one of the ways that sunglasses do that is filtering out some polarizations of light. So the sunglasses are a polarization filter. And it's not a direct analogy because this is a radio telescope and there's some complexity, but it's a bit like saying our telescope is like polarized sunglasses, and so we can detect polarized light as well as normal light.
In other words, it makes it through the filter, so to speak.
That's right.
All right, Doctor, we are out of time, and it was a pleasure talking to you, and I can't wait until you get your big survey going because I think you're going to find a whole lot more mysteries.
We're really excited about it.
Good luck.
Thank you.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing, and be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?